For those who don't know me, I'm Lucas Pinegonda. I am an expert for medical grade plastics, and I help MedTech companies to choose the right plastic for their application. I've worked in the plastic industry and in the MedTech industry for the last 10 years, built a lot of experience on sustainable plastics, material properties, material selection, medical device, and material compliance. And the goal of the next hour is to give you my paradigm of how to develop a sustainable medical device with plastic in an hour. So first of all, we need to talk about sustainability in general, because sustainability, that word, if you don't have a proper understanding of sustainability, then it is going to leading you down a path that you do not want to. Then we will be talking about eco-design and our eco-design framework with our 11 steps. We will also link further resources for eco-design because we have YouTube videos on that. Then we will talk about structured plastic selection processes and how we apply it. And then we're going to dive deep into what recycled and bio-based alternatives are there on the market. We're going to see some examples. And then at the very end, we will be talking about single-use versus multi-use, because that's also a topic that comes up very, very often. So let's dive into it. Sustainability in medical technology, or sustainability overall. The word sustainability is often used when ecology or more ecological is actually meant. So real sustainability actually means is the ecology, it's the economy, and it's the patient outcome. So if we want to translate that in medical technology, that means it's good for the environment, it's good for our pockets, and it's good for the patients, or even better for the patients. Because only if we can have those three pillars of sustainability, the environment, the profitability, and the patient outcome. If we can have those three pillars, then we will have a winning system and a good, viable medical device. So sustainable medical device does not only need to fulfill the better for the environment part, but it also needs to have the same patient outcome or even a better patient outcome. And it has to be profitable and ideally at the same cost, which is very, very hard to achieve. I'm very aware of this. I spend my days figuring out how to do that, but only if we can get all the three dimensions aligned, then we will have a winning system. Good. So what forces are moving MedTech or are moving any company towards more sustainability? And only if you understand like the forces that are moving your company, then you can actually achieve something and get your medical device or sustainable medical device developed. So the first is SBTi or self-commitments. Lots of these commitments are coming from investor pressure. So investors are pressuring companies into committing to science-based target initiatives. And what we found is that lots of MedTech companies already are SBTi committed. Then we have the competition acting, which is competitive pressure. What we see here is as soon as someone has something on the market that is your direct competitor, then the discussions really shift from, okay, how do we get this as fast as possible? Because before that, it was like, oh, will that really buy someone? Or will someone really buy this? And now as a competitor is on the market and is successful with it, what you will see is that it's a fear of missing out that is really setting in. And then we have the customer pressure. So healthcare systems like the NHS are pushing suppliers to be carbon neutral by 2045. And if you don't have a plan on how to get there in 27, you will not be considered as a supplier anymore. And that's like a very harsh and a very, very strong example of how customer pressure can work. But we see more and more that tenders in the Nordics and in the UK are more and more incorporating sustainability requirements. And then in the end, we have the regulatory pressure. Those who will not be moved by customers' competition or self-commitments, those will be moved by regulations. So what we analyzed is the 100 biggest MedTech companies in the world. And when you do that, you can check the Science Based Target Initiative website. and see if they have a commitment, if they either are committed or if they have verified targets. And if you go through that, you find that 49 of the 100 biggest MedTech companies are committed. And by turnover, if you take their turnover and sum that against the market size, you see that 60% of the MedTech market is already these 49 companies. Meaning that the MedTech space is rapidly committing to climate action. And like last year I heard this so many times. Yeah, sustainability is not a trend anymore. It's like now Trump is in office and sustainability is not cool anymore. But you know what happened in that last year? Like 10 of these big companies are committed to science-based targets. So the number increased from 39 to 49 in the last year, which is very telling. So it may be not in the news as much sustainability, but the corporate action is still there. And with the Science-Based Target Initiative, these companies are also pushing their suppliers to reduce their carbon footprint. And yeah, lots of these companies have the Scope 3. That is their biggest contributor. And materials are the biggest lever that you have in Scope 3. So therefore, this is the motivation why we want to look into sustainable plastics, because the materials make up a lot of the Scope 3 emissions. Good. What do we also see? We see lots of new medical devices coming out with sustainable plastics. So we have, for example, endoscopes with biocircular mass balance plastic in their handle. We see lab consumables with biocircular plastics. We see otoscope tips with mechanical recycled plastics, physical content bio-based. This is the BioVent circuit, something we helped co-develop. And then we see stuff like hybrid use solutions, such as this stapler where you can like detach the tip. And the second thing we see is that lots of recycling initiatives are popping up. So take back programs and recycling initiatives. So for example, Johnson & Johnson, Boston Scientific, and also Ambu, they have their own take back program. So they take back their used single-use medical devices and recycle them. And then we have stuff like Remit or Recipen or Vinyl Plus or the Healthcare Plastics Recycling Council, which are initiatives to get plastic recycled from medical waste sources. And we will dive into the topic of medical waste later. And what you also say that like there is a regulatory tsunami heading for MedTech. MedTech Europe did a report on how densely regulated the MedTech is in Europe. And what we see here is you don't have to read everything on this chart because it's like humongous amount of regulations. But the light green ones, those are the ones who have the goal to ensure the protection of the people and the planet, which is basically roughly sustainability regulations. So the ESPR, the PPWR, the Green Claims Directive, targeted revisions of stuff. And you see that this is a very huge chunk that makes up the regulatory density of medical technology. And some of this is only about to be entering into force. So the PPWR enters into force on the 12th of August. This year, the ESPR, it's not even clear how it's going to be done for MedTech. So what we see overall is that regulations are clearly pushing towards more sustainability, also for MedTech, but it's a little bit about, it's not yet here, but it's coming. It's many people say, but there's the omnibus and there's the simplifications going on. Make no mistake, the train is not moving at 300 miles per hour, but only at 100 miles an hour, but the direction is the same. It's going to be the same direction, and we're going to get sustainability criteria, eco-design criteria for our medical devices. So, with the motivation of why we want to do this out of the way, let's focus on how to solve this. And we can solve it in, I'd say, 3 ways. There is the design, there is the process, and there's the material. And with all 3 things working together, you will have a really sustainable device that costs less, that is good for the patient, and that will achieve your environmental footprint that is lower than before. But the design, and this is where I want to focus here, is that design plays a huge role for the cost and the ecological footprint of your device. It also influences the recyclability, if you can reuse this, the business model, and of course, the patient outcome. And therefore, what I want to go into is our framework for design for sustainability, which is an 11-step process, which we're going to go over in the next slide. But I do not have the time to go into every little detail here because, as I said, I had to pack so much information into this hour to make it viable and to make it as valuable as possible for you. Therefore, what I recommend is go check out our YouTube video, which is Master All 11 Sustainability Steps. This is the thumbnail, and here I put the link in. And what it basically does, it gives you a business, technical, regulatory, and environmental and user needs framework that is iterative and that will give you basically a blueprint on how to get to a sustainable medical device concept. Yeah. So in very short, how this will work is we will start with our use case. So before we design anything, we go and think deeply about the problem. Because the biggest problem that I see with medical device companies, with startups, with even bigger companies, it's like, we do X solution or we have X technology is the identification of yourself as a company. So, for example, I do injection molding solutions for a medical technology, but you shouldn't start with the solution. You should start with the problem. So lots of tech founders are like this. They have cool tech and they want to apply it somewhere. And then they have a hammer and everything looks like a nail. So you should fall in love with the problem and not with the solution. For example, if you find a problem like diabetes or dementia or anything that is a medical problem, fall in love with that problem and figure out how to solve it before you start designing anything. Then, this is very, very, very difficult for established companies, you should challenge your existing business model. Because lots of business models have the base assumption that you need to sell product. You need to sell single-use devices. And then you're incentivized to sell more than you actually would need to solve the problem. So if you challenge business models, and here I like to pull up the example that is geographically very close where I live, is the company Hilti. Hilti is a drilling machine company. They sell drilling machines, but this is not really, I'd say, correct because Hilti doesn't sell drilling machines. They have the best drilling machines on the market. However, they sell the ability to make a hole. So they have like a subscription-based model where you have always the ability to make a hole in a wall and you have always this many machines at your disposal. If one breaks, tomorrow you have a new one. So they're incentivized to maintain the machines, to make predictive maintenance, and to make the machines last longer and have a lower cost and environmental impact while still making the same amount of money. So same with single-use devices. If you could make it a device as a service or an outcome as a service, that will serve you greatly because it will decouple the material that you use and the outcomes that you can generate with it. Then if you're fixed on, okay, this is going to be our business model and this is a problem we're solving, then you will start to reduce whatever you do to the core function. I see this so often. The best thing you can do is just leave things out. Just avoid certain components. Just avoid certain functions. So why, for example, does a surgical device need to measure the temperature of the room? That's just an absurd example. So maybe there's a very good clinical need where you need the temperature of the room for your device to function. But if that is not the core function, you should avoid it. Because every bell, every whistle you add to your device, that will cost environmental footprint, it will cost. Then you should reduce the number of components, because less components means less injection molding tools. That reduces the cost, that reduces the environmental footprint. It makes it easier to assemble. It makes it easier to validate. And it will be I just recently had a podcast interview where he just said, and it's going to come out very soon, it's like, you just need to make an elegant device. So try to make the device as elegant as possible with the least amount of components and the least amount of design acrobatics needed to make it work. So if it's the simplest solution should prevail. And those are usually the ones that cost the least and have the least environmental impact. And then you start to optimize the components. There's lots of good software to do this. It's called the topology optimization software, where you only put material where it's actually needed and where it's actually stressed. You can also try to reduce length of tubes. So for example, if you don't need a 5-meter tube, you just need a 1.5 meter tube, make it 1.5 meter long. It reduces a lot of weight and reduces a lot of environmental footprint and cost. Then you should start to optimize packaging. With the PPWR, you will be forced to do so. And then you design for disassembly. So avoid anything that is gluing, that is welding, that is not mechanical joints, because if you can disassemble it, you can later recycle it. It's easier for repairability. And then we come to the point number 8, sustainable material selection, which we will go into detail later with our great match framework. So as a baseline, you only need the material, you only take the material that you actually need. Do not over-engineer. Just because PEEK will work doesn't mean that it has to be PEEK. It can also be a PA6 with glass fibers. That should work fine. And if you don't need a PA6 with glass fiber, it could also be a polypropylene. So try to use only that material that you actually need and do not over-engineer. Then design for recycling. Here, stuff like color, stuff like printing, multi-layer foils, multi-component designs such as 2K injection molding comes in. You should avoid these to make it better for recycling. We will make I will make a comment on, but medical waste isn't really recycled. Yeah, sure it isn't, because it's also not designed for it. So we will have to start somewhere. And then the step number 10 is supply chain. We can optimize that. We can try to pool materials. We can try to nearshore materials in order to reduce costs and environmental footprint. And the details are laid out in the video that I linked above. And then the most important point is the last point, the 11th point, because this is built on the lean principle, build, measure, learn. So you build a prototype, then you measure, and 11 is the step measure. You conduct a life cycle assessment, calculate your environmental footprint, although maybe initially roughly, and then you calculate the cost that is associated with manufacturing this, and you estimate the performance of your device. And if you have a measurement point for all three, then you know how close you are to an ideal solution. If you have a lower environmental footprint, a very low cost, and a good patient outcome, then you can stop. But before that, you will loop back and exercise all 10 steps through again, and then you will measure again. So you have an iterative design process that starts with a problem, ends with a supply chain, and then measures what is the outcome that we're going to get if we apply this. And if it's not good enough, we loop back. That is our framework of design for sustainability. Of course, there are other frameworks that you can use. There's other processes that you can use, but this is the one that we settle on, and that works pretty well. So now, how does material selection come in? This is the point number 8 here, sustainable material selection. How does one do that? And this is going to be where our core expertise is and how this fits in. The core material selection process, or a holistic material selection process, works like this. You define the product requirements, and that may be the performance criteria, that may be the risk class, what price, what the reimbursement is for this, features and benefits, where do we want to sell this to, so the markets, what are the patient safety requirements, and then biocompatibility will follow. And then what sustainability improvements do we want to make? Do we want to just make 30% better, or what are our CO2 reduction goals? What are our KPIs on the sustainability front? And then from the product requirements, we'll have to derive the material requirements, and we will have to translate this. And then we get to the technical, the economical, the regulatory, the processability, and the sustainability requirements of our material grade that we are going to use for our component. And this is where our framework for material selection comes in, because this is a process that takes you from, I kind of know what my product has to do, towards, okay, I will sample these grades because these grades are going to be suitable for my component. And what we do is we have a structured interview process. You will take up all the requirements, technical, economical, regulatory, processability, sustainability requirements. Then we find alternatives. So we gather a lot of data from databases, from supplier recommendations, from materials that are already in use. And then we compare them. And then we make a holistic value analysis, which are based on these requirements and how you rate them, how important you think those are. And then you will get a material recommendation in the end. And then, of course, like after the recommendation, you will sample, you will test. But I think the key step is the identification of the candidates and the rating against them, against each other. And here we have the giveaway that you're going to get when you send me a DM on LinkedIn so that I know who wants to have this. And we will send you the requirements checklist. This is a giveaway that we ran a few weeks ago with a LinkedIn post. And as you're joining this webinar, and I think you should be taking away a lot of value, we will give you this Excel, which is our requirements checklist. So the requirements that we are looking for when we select the plastic. And this is going to be an Excel. You can use it for your own projects. So we give it away for free. Just send me a DM and say, hey, please send me the recording, the checklist and presentation. And I'll get that to you. With the LinkedIn Live, I am not able to gather your emails or anything like that. So maybe the next webinar we're going to do over another tool where you can register with your email and then I can just send it out as an email. But currently we'll have to revert to this, send me a DM and I'll get it to you method. Good. So what results are we able to achieve with this framework? So on average, and this depends a lot on your volume, the plastic that you're already using, how good that plastic selection was, how good your supply chain is, how strict your procurement is on cost savings. But on average, for the recommendations that we did in the past, we uncover a savings potential of around 40,000 Swiss francs. You'll have to weigh this against the project that it takes to change a material over. So validating a part and validating another material is also going to be costly. So you'll have to calculate the ROI on this for yourself. But this is a good average number. And then we can also find, if your goal is more of a CO2 saving, we can find at least 1 kilogram of CO2 savings per kilogram of plastic. Sometimes we even find more, like 2.5 was also something that we found before. But this is like an order of magnitude what kind of results you can achieve when you systematically look through what is available on the market, understand what you actually need, and do not take more than you need. You do not over-engineer. And we can deliver a recommendation within 6 weeks. If you do this internally, usually it takes you longer, but we're trying to push that down with a lot of automation we're aiming for 2 weeks, but we're not there yet. It's like 6 weeks. 6 weeks is what we can guarantee right now. In the future, we'll be faster than the 6 weeks. Good. So, and if you apply the design for sustainability and the structured material selection process, you can achieve something like in this case study from Röchling. They did design this part for sustainability, which is a trocar. The function of a trocar is to make a hole in a body and keep that open for minimally invasive surgery. And what they did is they optimized the design, reduced the amount of components from 12 to 8, which is, okay, you now have to buy 8 injection molding tools instead of 12. And if you make that like an 8-cavity mold, that's like 4 times 50,000 right there in savings. And then they saved like roughly a third of the material by topology optimization. The design for this assembly, so all components are now mechanically separable. They went for a downgrading from polycarbonate, PCABS, and a variety of materials to PLA and polypropylene. So there are only 2 materials left. Everything is polypropylene and PLA where you need the stiffness. And then they designed for recycling. So minimal variety of material, clean separation, reduction of printing ink, etc. No 2-component injection molding. And with that, they could achieve a CO2 reduction of 50 to 51%. So 51% CO2 footprint less than before. And this is the order of magnitude that you can achieve with such a system without going for a multi-use, without going for a different business model. So this is just if you optimize this design as much as possible with the right materials, with the right processes, you can get around half of the CO2 footprint out of your material. And this is a number that pops up a lot. I saw different case studies where you see a similar number, around 50% of CO2 reduction. Good. Then now we have the design part. Now we have the selection part. Those are the things that you need to implement. You need to have an eco design process. You need to have a structured material selection process in order to design properly. But then you need to also understand, okay, what kind of materials are available on the market. And this is now the second part of the webinar, where we're going into recycled and bio-based plastics. What is there on the market and what terms do you need to understand in order to have an overview for what sustainable plastics are there for MedTech. So first of all, we need to talk about the feedstock of a plastic, which is basically the base material that the plastic is made from. The default until now was fossil feedstock. And if you want to reduce the dependence on fossil fuel, if you want to reduce the CO2 footprint, you need to go away from fossil feedstocks towards recycling or bio-based feedstocks. There is carbon capture. Currently, this is not what we see popping up on the market. It's not viable because it's extremely expensive. With cheap green energy becoming a reality, this can be more viable in the future. But currently, we don't see a lot of carbon capture materials. The 2 most viable ones are recycling and bio-based. And here we have to differentiate. Recycling isn't recycling. So there's mechanical, there is physical-based recycling methods like solvent-based recycling, which is the main one, and the chemical recycling. So recycling isn't recycling, and we will go into that. And then bio-based can be biodegradable or drop-in solution, which is same plastic, but we will also look into the bio-based in more detail. Good. We will start with the recycling topic. And if we talk about recycling plastics and medical technology, two topics pop up. Number 1 is recycling plastics in medical technology. So use of recycled plastics in medical devices, for example. And the challenges here are the quality and risk management. This is usually an upcycling, so it's difficult to get plastics that have the quality and risk management that we need for a medical device. And we will see an example where this has worked. And you will need to combine this with eco-design in order to make then this medical device also recyclable as a medical waste. So the second topic is medical waste recycling. Medical waste recycling is a huge topic, and what we see is that healthcare professionals see recycling of medical waste as a sustainable or as the sustainability problem. So what we see is that if you talk to hospitals, if you talk to clinics, they will oh yeah, we need to do something about all this waste, because that is what they, in their heads, sustainability means, is they think less in CO2 numbers, as we do in like MedTech corporations, and more in, oh, how do we reduce the waste? Because waste is visible, it costs them a lot, they're liable for it, and it's difficult and complex to recycle waste, and usually it's incinerated. And how do we do a recycling of medical waste is what we've proven with these take-back systems of J&J and of Ambo and everything, is that it's possible. The logistics and the bureaucracy is difficult to navigate, but it's possible. But the biggest challenge is logistics and decontamination. So how do we make sure it's safe, and how do we transport it from A to B without it costing a fortune? Currently, it costs a fortune. And usually this is downcycling, because if you bring that to a recycler, J&J, I think they have collected like 4 tons of plastics in the last 4 years with their stapler recycling. And what they see is that they go to a recycler and say, hey, we have these 4 tons of plastics that we would like to recycle with you. What do you say? And they say, yeah, cute. Come back when you have 100 times more. That is like the reality, that we need a lot of volume. And then in order to make the volume work, we need to figure out the logistics in a cheap way and in a reliable way and in a safe way in order to make it work. Good. So can we use recycled plastics in medical technology? What are the pros? What are the cons? What are the challenges? And what are the different recycled plastics, and how viable are they? And how do we actually do this? So this is an example. It's an otoscope tip that goes into your ear canal. So it's a class 1 medical device with patient contact, and they made it work with mechanical recycling. And to understand, can we use recycled plastics in medical technology? It's like, yeah, number one is which recycled plastic? And secondly, what is medical technology? Because medical technology, I use this analogy a lot, is between crutches and an implant. So a crutch, like if you take the mechanical parts of a crutch that has no patient contact, the mechanical requirements are the harshest ones. And here we can make it work with a mechanical, recycled, post-industrial, post-consumer recycled material very easily, because the worst thing that can happen is the crutch breaks and the patient breaks its leg again. So we can make sure that the material has the strength, has the durability to work in a crutch, but a crutch is not an implant, not a 15-year implantable device that will stay in the body for basically forever. And here we see that there's like 5 to 10 medical device or plastic companies that actually offer implantable material. So lots of virgin suppliers don't dare to supply into implantable applications. So why should we go there with recycled materials? So yeah, the question is where is the application boundary? So where do we have to stop using recycled material, and where do we have to start using virgin-like material? That is the question that currently is, I'd say, unsolved, but it also depends a lot on what you mean by recycling material. And here you will see the diversity of recycling methods. If we have a plastic product, it reaches its end of life. Then you collect it, you separate it, and then you have a different, let's say, buckets where you can put it in. You can put it in mechanical recycling, which is what people usually think of as recycling. So you take your PET bottle, you throw it in the PET bottle bin. It's one material, it gets shredded, it gets made into a bottle again, and then it is recycled. So this is what people usually mean. But this is like not possible for all the medical waste. Sometimes it's a multi-layer foil, then you can't do that. Then you would need a dissolution technology or solvent-based recycling. You solve the multi-layer foil, you take one plastic from the other one by different solubilities, and then you separate it like this. So it's a physical recycling method. And then we have the huge bucket of chemical recycling. You can do chemical recycling via enzymes, via solvents, via breaking them down in lower molecular weight components like pyrolysis or gasification, or you can incinerate everything and then carbon capture the CO2 and make chemical components, chemical substances out of the CO2 again. So mechanical recycling is a huge field, and therefore like the quality and the environmental impact of these methods is not the same. So that is very, very important. And with this application that we show here that is a 100% recycled polystyrol from fridges. That's usually a high impact polystyrol that is very uniform. And there is a good supply of fridges that can be recycled and that yield the same quality consistently. It's a class 1 single-use medical device, and it has direct patient contact. And from the material use, not an overall LCA, because I haven't seen an LCA of the whole tipped device, but just from the material, which is usually the biggest part, you can save 2/3 of the CO2. And then they produce all of this with green electricity. They have unbleached cardboard as a packaging. So this is an example where we see mechanical recycling in application. So this is the proof that you can get through MDR with recycled material. Of course, there's a lot more to this, but I'll have to skip some details here. We also see a lot of chemical recycling in packaging. But as said, in order to pack as much value in here, I'll have to keep it at that for recycled plastics. Because now we want to go into bioplastics, which is actually the one that is most used in MedTech, what we see the most. So if you talk about bioplastics is a very imprecise term because you have bio-based and then you have biodegradable and then you have compostable. So what we see here on the y-axis is bio-based and fossil-based. And this is not a binary. This is a gradient from 0 to 100. So you can have 100% and you can have 0% bio-based. And then this biodegradable, which is generally very slow biodegradation on the polyethylene and polypropylene side. Just by the way, polypropylene and polyethylene do biodegrade over time, like 7 years, 10 years until they biodegrade in the environment. And then you have something like PBAT or PHA, which biodegrades a lot faster. And this is a material property here. So this is also a, let's say, gradient from slower biodegradation to faster biodegradation. And then you have the term compostable. And what I usually say in this regard is like, okay, a tree trunk is biodegradable. We can all agree that wood is biodegradable. But if you take a big branch and throw it on your parking lot, well, it's going to stay there for a while. So it depends all on the wall thickness, on the environment, on the humidity, on how fast it's going to biodegrade. So, yeah. This is the space of bioplastics. We can part them into bio-based and biodegradable. And there are 4 quadrants. And we are going to look at bio-based firstly. So the ones that are at least a few percentages bio-based. And for that, we need to look into, okay, what are the feedstock generations here? Because you can have generation 1, which is food, which is corn, sugarcane, everything that is exclusively cultivated to produce plastic from it. And then is the second generation, which is usually also called biocircular feedstock, which is food waste, like used cooking oil, sugarcane waste. Tall oil is also one from wood production, so a waste product of wood production. And then there's, I think, the future, which is biotechnical solutions like algae and bacteria, which tend to take CO2 from the atmosphere and directly convert them into feedstock directly or over a, let's say, bacteria route. So the ideal solution would be like we fill the Sahara Desert with a bunch of tanks that produce oil-like substances via capturing CO2 from the atmosphere. But we're not there yet. This is not scaled. Generation 2 feedstock is the best from an environmental perspective that we can get. Most of the bioplastics are generation 1 feedstock. And then now we see an application of this. This is the BioVent circuit. That's something that we helped co-develop with Galmet, and they put this on the market as the first anesthesia and breathing circuit that is bio-based, and it's 48% bio-based with physical content. What we did is we replaced the polypropylene with a bio-HTPE and then reduced the EVA content to LDP ratio in order to get a better environmental footprint. And with that, we get, as said, 84% physical bio content and close to 1 kilogram of CO2 reduction from cradle to gate. So we have this question in the chat from Kirsten, cradle to gate or cradle to grave. All the calculations we show, I think, today as cradle to gate, not to grave. Also because it's very difficult to get the transportation paths accounted for, because usually like Röchling and Galmet, those are contract manufacturers. And then knowing where the transportation ways go and how the end-of-life scenarios are is very complex to navigate. I understand that cradle to grave would be better, but those are cradle to grave comparisons. Good. Then when we talk about bio-based, we need to explain what mass balance is, because this is a very misunderstood topic. This was physical content. Then we have the most prevalent one, which is mass balanced. So we have bio-based or biocircular feedstocks, which we put into the plastic manufacturing supply chain. We have chemical recycled feedstock that we put into the plastic manufacturing supply chain. And we have fossil feedstock, which we put into plastic manufacturing supply chain. And in order to keep track of it and to use the same assets, because let's be honest, plastic manufacturing plants are huge. They cost billions and they're like little villages or even bigger villages in terms of size. You do not build a new one just to produce bioplastic. You take the existing one and use different feedstocks to produce the same plastics. And in order to keep track of it, what they do is accounting. So you see it's like a light blue arrow, and then here's a dark blue arrow, and in the middle there is a mixed blue arrow, because they are all in the same stream. And then you send it to the converter, you send it to the MedTech company, and then you have, in the end, you have a certified product, and you send that to a healthcare facility like a hospital or a lab. And in order to make sure that nobody cheats, you have the ISCC Plus, the International Sustainability and Carbon Certification, which is the ISCC Plus certification, which everybody in the supply chain has to get in order to make sure that nobody cheats and no double accounting is done. So we have these three chain of custody models, which is physical segregation, which is what we saw in the first example from Galmet. And then we have the mass balance example, which is physical content needs to be possible, and it needs to ensure that no cheating is done over bookkeeping and over third-party certification. And there's the third one, which people usually confuse with mass balance, and this is book and claim. And book and claim is what we in layman term call certification dealing or certification trading. So you make biofuel in Brazil, you fuel your car with the biofuel, and you do not take credit for the carbon reduction. You just pay the normal fossil price. And then this certification, this offset, is traded to a airline in Europe who does CO2 compensation. That is what people usually object to and call greenwashing. And mass balance is a certain physical content has to be possible. So the bio and the fossil are used in the same plants. Plants meaning chemical plants. Good. What can you achieve with mass balance? This is a project that where we helped Hamilton to introduce the ISCC Plus certification, which we also helped. And the lab automation tips, the Core 2 tips that they have here at the green line, they called it the green line. This reduces the CO2 footprint cradle to gate by 84% by switching over to a biocircular feedstock. And this is the LCA they did comparing their different sizes of the tips. And they were very happy with the support that we did for them. So this is what you can do with mass balance. And this is what you see pop up with a lot of these lab consumables. So I know that, for example, also Eppendorf has ICC Plus certified tips. There's lots of medical device companies who are using ISCC Plus certified biocircular feedstock, for example, also Ambu with their handles for the endoscopes. And yeah, so this is a very common solution that you find in MedTech. Good. Biodegradable plastics. I'll need to speed up a little so that I can get to the multi-use, single-use. And just be sure that you ask your questions. I will stay on a little later for the questions. Just type your questions in the chat that you have as you go, and I'll try to answer them all in the end. But I will probably just finish at 11 with having the webinar. So, biodegradable medical device. I have a strong take on it. You might challenge me on it, but currently, medical device are incinerated. Like, this is the gold standard of medical device. I don't say that this is the best way of doing it, but if you use a biodegradable plastic for a medical device, you'll get a bunch of problems. And we tried, and this is the problems that we found. So number one is, since they're degradable, they usually have a poor chemical resistance against solvents, against disinfectants, against sterilization. This makes it a problem. They tend to break down and degrade, and this is the, let's say, side effect of it. They break down and they have poor chemical resistance. Processing can be difficult. So if you have them in a hot barrel in injection molding, they also tend to break down and lose properties. And due to their ability to degrade over time, the shelf life and the accelerated aging is usually the harshest criteria. So if you want to have 3 years of shelf life, then biodegradable plastics will just like be brittle and fall apart and break down into dust basically when you age them for that long. They're usually very biocompatible, so this is a good thing, and they have a good CO2 footprint due to them being bio-based usually. And in some applications, they have really cool clinical benefits. So for sutures and for implants, you can use biodegradable plastics since they also bioresorb, which is a very interesting fact. So there are implants from PLA, there are sutures made from biodegradable plastics that will dissolve in your body and have cool clinical benefits. So in short, I would not recommend using a biodegradable plastic that breaks down over time very fast. Something like a PLA can be viable since PLA also has the tendency to not break down as fast as other polymers. But usually, like if you have good chemical resistance requirements or have long shelf lives, biodegradable plastics do not work as well. So I would usually go for a drop-in solution like a bio-PE, like a biopolypropylene that we showed before. Good, then, when do I take bio-based and when do I take a recycled plastic? This is a heuristic, but it illustrates a point. If you have the 3 classes of plastics, the commodities, where we take a polypropylene, the polyamide PA6 in this case, or PA66, for the engineering plastics, and for the high-performance plastic, you take PEEK. And if you take the product carbon footprint, cradle to gate, and compare bio-based with biogenic carbon, and then you take mechanical recycling and then you take fossil and compare them to each other. So with the polypropylene, you'll land round about at 2, give or take, it's a heuristic. Then with the polyamide 6,6, it's around 6.6. And with a PEEK, you're around 20, 25, depends on the supplier. And if you take a bio-based, you'll usually save the biogenic carbon. That is what you get. And for the kilogram of plastic, it depends on how much carbon you have in there, but it's usually 2.5 to 3.3 kilograms of CO2. For polyethylene, it's 3.14 kilograms of CO2 that you save. And with that, for a polypropylene, you'll get negative cradle to gate. I know some people have a problem with negative cradle to gate impacts, different topic. What I want to illustrate is that the saving that you generate with a bio-based plastic with a commodity is a lot in terms of percentage. And then if you make it mechanical recycling, you will get something between 0.3 and 1 kilogram of CO2, meaning that the reduction isn't as great for recycling commodities. If you start with engineering plastics, that will be greater than the bio-based. And if you take it up to a PEEK, bio-based doesn't even scratch the surface. It's like 10%, 15% CO2 reduction. If you recycle it, then it's like 95% CO2 reduction. So the more valuable, the more energy intensive a material is, the more sense recycling makes versus being bio-based. So that is my takeaway. The higher up you go, the plastic pyramid, you should go for recycling more, or recycling makes more sense. And if you are in the commodity space, where we see it also in application, usually bio-based drop-in solutions are, from a CO2 perspective, better. So single-use versus multi-use, that's another topic that I hear a lot. My take is that there's no one right answer. For a very complex and very costly device, it makes sense to make it multi-use. For a very simple and very cost-effective device, it makes no sense to make it multi-use. So multi-use syringes usually don't make sense. Multi-use catheters, endoscopes, CTs, ventilators, those things make sense multi-use. Also depends a little on how do you design that. I know this is a heuristic, so this is a rule of thumb. So at some point, there's a tip over point. And if the reprocessing cost and the environmental footprint is higher than the production cost, then you should go for a single use. And this is where I see it. It's usually around, let's say, 100, 200 euros per device, where it starts to make sense to make it multi-use. This is, as said, the rule of thumb. But it's like for very complex and costly devices, it makes sense. And then for very simple devices, it makes no sense. And there's like a third option that I like to propose is a hybrid use device. And this is the Medtronic Signia. So this is a stapler, which usually ends up being a hybrid use, a complex medical e-waste that is contaminated with a lot of electronics and computers in here. And instead of throwing out the power unit, you can only click off the tip and then reduce the waste by around 2/3. And this is a very, very cool device. So you have a single-use component, then you have a multi-use component that you can reuse. So that is something that you should also look into. And that will be it for the webinar. So I'm sure you have a lot of questions, and I hope that this brought value to you. So if you have more questions, I can offer you the following. So you can scan this code, and with that code, you can book a call with me. I took some time that I reserved for questions for this webinar in the next 3 weeks. So next week, I'm going to be on a vacation, but this week and the week after, I reserved some time. So what you do is you scan the code, you select the time, you book a call, and then you show up with your questions, and I will answer all of them. So of course, like if this leads to a collaboration, cool. I would love to see that happen because we burn for making medical device more sustainable. So check that out, book a call with me and bring all your questions that you have from the webinar, or even if you have inputs. I love feedback. And what other value can I give to you? So there's my YouTube channel and there's my Spotify podcast. We have lots of interviews, for example, with Ambu, with Thomas Kegi about LCA, about documentation, about the green premium on ICC Plus certified materials. So all of that, check out those two, subscribe to this, also subscribe to my newsletter that is on my website so we can help you make your medical devices more sustainable.